Now we already defined displacement and then velocity as a displacement over an elapsed time, leading us to the next quantity that we're going to be interested in, which is the acceleration. So an average acceleration is going to be the change in velocity over some change in time. An instantaneous acceleration is going to be that same, change in velocity over a change in time, but in the limit as delta t goes to 0, telling us once again that we understand that there's an acceleration that exists at a given instant. We don't have to calculate an average. In terms of units, because velocity has units of meters per second, and we're taking a change in velocity over a change in time measured in seconds, our units are going to be meters per second squared. That'll be useful to you for checking answers, and also when you're given a quantity, if you see that it's in meters per second squared, you understand exactly what it is. In the same way that we were calculating this instantaneous velocity by looking at the tangent to a graph of position versus time, we're going to look at an instantaneous acceleration as a tangent to a line plotting velocity versus time. We need to consider sign conventions pointed out here that when that acceleration is positive, your velocity is increasing, and when you're decelerating or you're braking, you're going to have a negative acceleration. Or if you see a negative acceleration, you know that your velocity is decreasing. What these pictures are trying to show us are the ideas of acceleration and deceleration, or a positive acceleration versus a negative acceleration related to the direction of travel. So when we look at this first case right here, we see that there's a car traveling from left to right. Its velocity is initially v1 sub x, and it increases. So this car is accelerating. It's going to have a positive acceleration as indicated here. If that same car had an initial velocity, as shown up in the upper right here, has an initial velocity, but then as it travels to the right, its velocity is decreasing, well, it's braking or it's decelerating. And so it has a negative acceleration, or as you can see here, the acceleration is to the left. Then there's the case here in the lower left-hand side where I have some car traveling initially to the left with a negative velocity, and the magnitude of that velocity is increasing. So it's accelerating to the left. Now notice that its speed is increasing, but its velocity is just becoming more and more a negative quantity. And then finally, this last case we can consider is car moving left, has an initial velocity which is pretty large in magnitude, or has a large negative velocity, and it's slowing down. That is, the magnitude of its velocity is decreasing. So it's going slower to the left. Well, in that case, it's actually accelerating to the right. So whenever you have a car traveling in some direction and the magnitude of its velocity is decreasing, then the acceleration vector is going to be in the opposite direction to its direction of travel. A lot of cases to consider individually, but as we work through problems, you'll become more familiar with it, and it will make sense. Here we see this graph of velocity versus time, and you'll see that some initial t1 here at A, we have an initial v1. And then at some later time t2 at position B here, we're going to have a new velocity v2. And we've discussed this in our definition of the acceleration, that you can look at the slope for an average acceleration. Look at the slope of a line connecting these 2 points when you have a graph of velocity versus time. So this should start to look familiar because you've done it in a similar way with velocity and you've done it with acceleration. If you want to calculate an instantaneous acceleration, well, you just take this graph and you take this point A and you draw this orange line here, this tangent to the curve at that point. And when you do that, if you calculate the slope of that tangent, that will give you that instantaneous acceleration.